In this section, we're going to be talking a little bit more about mass and energy conservation. We've already done a bit with this, but take a quick look at this situation. Because mass is always conserved, and we're assuming that fluids are basically incompressible, we're going to assume that the volume of water going in at point 1 must equal the volume of water coming out at point 2. And if you remember just a little bit about your math, hold on, let me talk a little bit more about this real quick. Before I do that, I should introduce flow rate. Flow rate is the change in the volume of fluid per unit time, and it's represented by capital Q. Because we know that mass and because density is constant for incompressible fluids, we're going to say that the flow rate at point 1, that's the flow rate into this thing, must equal the flow rate out of it over here, which is Q2. That is, if you put a liter of liquid in at this point in 1 second, a liter of fluid is going to leave at the other point in 1 second. Now, let's assume that this little blue shaded region right here is the volume of water going in. What's the volume of this? Well, it's the area of this one side right here times x1. And that area over here is a1. So what can we write in this case? Well, we know that the flow rates in equals flow rate out. We can actually replace the volume going in, that's V1 right here, with A1 times x1. And again, quick reminder for the cylinder here, the volume of this cylinder is just the area of one end cap times its height, which in this case is x1. We're going to do the same thing on the other side, except in this case, we've got this area here times the thickness, and I know there's a little bit of perspective here, but this volume or area here is A2, and so we've got A2 times x2. And now there's something interesting going on here. If you don't already see it, what is x over t in both of these cases? Well, hopefully you'll recognize it right away. Displacement over time is just velocity. And so we can rewrite it this way. Area times this quantity, here's where our deltas go, equals area 2 times this quantity, which you can then write like this. And this is the equation of continuity. A1 times V1 equals A2 times V2. Intuitively, it's interesting. What happens if the area gets smaller? Well, then the velocity must get larger. And most of you before have realized, you've got a garden hose and you want it to spray further. What do? You put your finger over part of the hole. What does that do? It reduces the area that's open and increases the velocity of the water that comes out of there. And so we're intuitively kind of familiar with this equation of continuity. So here's a quick multiple choice question about it. How does the flow rate compare in section 1 to section 2? Well, just a quick notice on this one. Notice section 1 has a much larger cross-sectional area than the other section. And you could actually figure it out in this case. What do we know must be true? Well, as the area gets smaller, the velocity must get larger. So over here we've got some small velocity. Over here, I guess I should call it V2 just to clarify, the velocity has to get larger because it's flowing through a smaller area. In fact, for those of you who are really observant, you're like, wait a second, if we call this area A, this area here, 4 pi r squared, is going to be 4 times the area over there, which means this velocity is actually 4 times larger. We don't actually need that, but what do we know has to be true? Well, the flow rate has to be the same. We don't lose any volume per unit time, so it's got to be A or B. And what do we know is true about the velocities? Well, V1 is going to be smaller than V2. Correct answer on this one is B. So mass conservation leads us into the equation of continuity. The volume of water going in must equal the volume of water going out. But we can also use energy conservation to come up with another law. Here's Daniel Bernoulli, a sketch of him. a series of very famous Bernoullis in mathematics, engineering, and science. Daniel was the one who came up with what's credited for this fluid flow equation. Where does it come from? It comes from the energy that a fluid can possess. So if you think about the energy, we've talked about kinetic energy, gravitational potential energy, elastic potential energy, even work is a form of energy. Can you do work on a fluid? The answer is yes. Can a fluid have kinetic energy? Yes. Can a fluid have gravitational potential energy? The answer is yes. And so the total energy is actually the sum of those three terms. And you might say, wait a second, what about elastic potential energy, 1/2 kx squared? Well, again, remember, in this unit, we're assuming that water or all fluids are basically incompressible. And so we're going to assume that there is no elastic potential energy. So it's just going to be those three. So plugging in our equations, kinetic energy 1/2 mv squared, gravitational potential mgh, work, force times displacement times the cosine of theta. I'm going to leave the cosine out for clarity. And what do we know? The sum of those three must be conserved, because energy must be conserved. Now, for no apparent reason whatsoever, I'm going to divide each term by volume. And you're like, oh, wait, why would you do that? Well, there's a little trick going on here. Mass over volume, if you remember back from the beginning of this unit, is density. So we can replace both of those terms with density. The one that's a little bit more obscure is this one. Distance over volume. And you might have to think about the units. Displacements measured in meters, volumes measured in meters cubed. So when we divide these, what do we end up with? Well, we just end up with 1 over meters squared, which is basically just the area in the denominator. So we can rewrite it this way. And you're like, whoa, wait a second. Where do we go? Well, kind of an intermediate step here that I should have put in. This gives us basically force over area. And if you remember from our definitions, force over area gives us pressure. Bernoulli said these three terms added together for any fluid have to be constant. So the sum of these three at one point in the fluid has to equal the sum of these three at a different point in the fluid. In general, he wrote it this way. Here it is, the pressure at one point in the liquid plus rho GH plus 1/2 rho V squared at one point unit or fluid must equal pressure plus that in the other point liquid. And this is called Bernoulli's equation. And it allows you to solve amazing things, like, for example, why planes fly, why water streams do certain things, why curveballs work. And let's take a look at a real practical example. Well, first of all, before we do that, here's our definitions. Again, we're going to use gravity as 10 newtons per meter. Pressure here is really atmospheric pressure. And take a quick look at this. So here's a FET simulation. And as we talked about before with the equation of continuity, velocity gets faster when the pipe gets narrower. But I also want you to look at the pressure here. So the pressure at this point in the pipe, I'm trying to get it to as close to the point as possible, is 118 kilopascals. Here where it's moving faster, the pressure actually decreases. And then if you go back to the area where it was the same as before, it goes back to roughly 118. I gotta find it again. Right there it is, close enough. About 118. It goes back to the same pressure. When a fluid speeds up, the pressure decreases. When it slows down, the pressure tends to increase. And this is a direct result of Bernoulli's equation, which I've written kind of vertically over on the side. So let's take a look, and here's my practical example. Points 1 and 2 are at the same height in this pipe. And the pipe starts out with a diameter of 2d on the left side, d on the right side. We've got a point 1 here and a point 2 here. At point 1, the velocity of the fluid is 5 meters per second. And we're getting the density, And we're given that those 2 points are exactly the same height. And the first question I have is, what's the velocity over here? Or I'm about to ask it. What's the velocity at point 2? So using the equation continuity, which I don't have written on the top of the page, it's pretty straightforward. It's just a1v1 equals a2v2. Please remember again, the area is going to be pi r squared. In this case, because the radius is twice as big, the area over here is 4 times the area of the piece over here. Doubling the radius, then squaring it makes it 4 times larger. So just plugging it in, the radius over on this side is going to be 2d divided by 2, which is d squared. Over here, it's going to be d divided by 2 squared. And the original velocity here, v1, is going to be 5 meters per second. And we can figure out the velocity over here. And some of you might say, oh, it's obvious already. It's going to be 20 meters per second. And you'll be absolutely correct. Why? The area became 4 times smaller, so the velocity has to get 4 times bigger. And now, using Bernoulli's equation, what's the pressure at point 2? We're given the pressure over at point 1 is 300 kilopascals. So plugging in what we know. Well, first of all, you might say, wait a second, how'd you get rid of the heights? Well, we were told that these two things are at the exact same height. So what did I do? These two terms would be exactly equal to each other. I subtracted them from both sides. Plugging in the numbers we know, the pressure over on this side is this. The velocity here is 5. Density is 1,000. We're trying to find this pressure here, and we know the velocity over on this side at point 2 is 20 meters per second. Solving the numbers gives us that. We're solving the pressure then. We get this, 1.13 times 10 to the 5th pascals, or 113 kilopascals. Bernoulli's equation, pretty doggone easy. One last thing I want you to realize on this one, we went from 300 kilopascals down to 113. Notice because of the greater velocity, pressure tends to increase, assuming we don't have a height change. And this leads us into this multiple choice question. 4 tubes here, each have one section of radius r and the other section of radius 2r, and they're at different heights. And we've got points x and y. In which of the following diagrams shows a configuration where the pressure at point y must be greater than the pressure at point x? Well, for the pressure to be small at point x, we need one of two things. We need a large velocity, which would tend to lower the pressure, or, I'm trying to write large over here, or the fact that it's at a small height. The greater the depth, the greater the pressure. So in which of these cases will x have a large velocity, and will it be at a small depth, basically a small h? If you look at these, to get a large velocity, we need x to be in a narrow spot. So this is reasonable right here, and this is reasonable right here. But in which of these cases are we guaranteed it's going to be a lower pressure? Well, if both these aero conditions are met, we're almost guaranteed. So which one is that going to be? The answer is C. Not only do we have a greater velocity, but we also have a small depth. We don't have that greater height change down at the bottom. Take a look at this one, another multiple choice. This one a little bit more mathematical. A fluid of density rho is flowing with some speed v1 for a horizontal section at area A1. I don't know how much I wrote on here. I better behave. It then splits into two smaller vessels as shown. So part of the fluid goes this way, part of it goes this way. As shown the pressure of the fluid in the region where the cross-section there is P1 and P2 respectively. Which of these is equal to the pressure difference? Okay, so the pressure over here is P2 in both of these, apparently, because they're both area 2. And over here, the pressure is P1. All right, so we're looking for a pressure difference. We're given that they're the same vertical height. We're looking down apparently from above. It's a top view. So we're taking out that and rearranging this equation. Again, we're subtracting this from both sides. We're looking for the pressure difference. So moving P2 or moving P1 to this side and then moving this term to the other side, we end up with this expression. Plugging in our numbers, we first of all have to figure out velocities. We know that the velocity here times area A1, where this is A1, has to equal the velocity over here. Now, technically, I've got two A2s over here. And so you'll notice in my equation here, I wrote 2A2 times V2, where V2 is the velocity for each one of these two tubes. It's got to be the same because we're reducing down to two identical tubes. Solving it then, the velocity there at or V2 is going to be equal to this expression. And unfortunately, we can't really do too much with it. So what do we end up with this? The pressure difference is going to be equal to 1/2 rho V1 squared minus 1/2 rho. And in place of V2, I'm going to put the expression we just came up with, which is relatively hideous. Solving that, you can actually factor out a 1/2 rho V1 squared from the top, if you can see it, and we end up with that. And then if you factor out the 1/2 rho V1 squared from both terms, and it may not be obvious, you'll end up with AP's answer, which is letter B. Not trivial. A lot of math. So here we have an actual AP free response question that involves Bernoulli's equation. You've got an underground pipe that's down here. It has a point A in it down right over here. And the cross-sectional area is this at that point. And then it goes up to the ground where it narrows. It's half the area here. And then we're given the velocity of the water at this point over here at point B as well. Calculate the speed of the water at point A. So for this one, we're going to be using the equation of continuity, which I didn't list on this slide. But we're working with this. We have the area. We know the velocity when it leaves the pipe up on top is 8.3 meters per second. 8.2 meters per second. And so we can very quickly calculate what the velocity is underground to find this. If we solve it real quick, area underground is this. Area above ground is this, where the velocity is this. We can solve for the velocity underground, and some of you can see it real quick. Because the area is twice as big, the velocity is half as large, so 4.1 meters per second. Calculate the absolute water pressure at point A. So here's where we have to use Bernoulli. And I'm going to set, just for our own sanity, H equals 0 down here, so I don't have to deal with any negative numbers. If I do that, we can actually solve this. Using Bernoulli's equation, here's all the quantities for point A. Here's all the quantities for point B. And we can plug in what we know. One quick note on this one, the height then at this point is going to be 0 because I defined the height there. The velocity was 4.1. That was the answer from the previous question. At the surface, we're assuming air pressure. So this pressure right here is atmospheric pressure, which you can remember AP does 100,000 pascals or 100 kilopascals or just 10 to the 5th pascals. The height at the surface is that, and the velocity when it leaves was given to us at 8.2 meters per second. If you solve that, you'll get 130,000 pascals or 130 kilopascals. Calculate the maximum height above the ground that the water reaches upon leaving the pipe vertically at ground level. Here you could solve it either by doing kinetic energy equals gravitational potential or use one of our kinematics equations. I'm going to go ahead and use one of the kinematics equations. What's the final velocity when the water reaches its highest point? Well, it briefly stops before it falls back down to the ground. I want to figure out at what height that occurs. So in this case, I want to know At what height is the final velocity of the water 0? We know it's leaving the ground at this. Gravity is going to make negative 10. And if you solve this, you'll discover that it's going to stop when it gets to 3.36 meters above the ground. And that's when it's going to fall back down. Calculate the horizontal distance from the pipe is reached by the water if it's launched at 60 degrees. So for this one, I'm going to erase this just for clarity for a second. We actually have to do a little bit of trig. So assuming this is the water that's leaving at 8.2 meters per second at that particular angle, we can break that into its horizontal component, 4.1, and its vertical component, 7.1. How do I get those numbers? Just by using trig and the 60-degree angle down here. First thing we always have to find out is, hey, when is this water going to reach the ground? Not realistically drawn here, but what do we know is true when it hits the ground? Well, its y position is going to be 0 again. Remember, the origin of the water is always 0, 0. So using the y equation for projectiles, initial vertical velocity is this 7.1 number right here. That's just from up here. Gravity, negative 10. And it looks like a quadratic, but you can actually factor out a t. T equals 0 is one solution. And you'll get 1.41 seconds is when it's going to strike the ground. That's interesting in itself, but we actually want the horizontal distance. How do we find that? Well, we use the x equation. There's no acceleration in the horizontal, so it's just the initial horizontal velocity, which is going to stay the same all the way across, times time. In this case, 4.1 meters per second, that's from up here, this number right there, times that 1.42 seconds we just solved a moment ago, and we'll discover that it's going to land 5.82 meters away from where it starts. These last two questions, C and D, are just using kinematics. It's only the first two, A and B, that involve some of our fluid equations. There's a little bit more another interesting situation I want to talk about, and that's with this particular kind of situation, a very simple one. A container that's filled with water, and the question is, what velocity will the water exit that hole? Now, we're going to assume that the hole is fairly small. Why? So I'm going to look at these 2 points represented here by sort of green diamonds. The air pressure at both of these points, they're both exposed to the atmosphere, and when we're talking about this pressure right here, we're talking about the pressure just outside the hole, not inside the container, but outside the hole. Both of these are going to be at atmospheric pressure, both P1 and P2. Since they're both the same quantity, I can subtract them from both sides of the equation, and at that point, we can simply come down to here. The question now is, I'm going to call, since I already made this P2, I'm going to call this V2. The question is what's the height? Well, again, just for our own sanity, I'm going to set the height equals 0 right at this point. Just makes it easier. We don't have to worry about any negative signs. I could have set it at the tabletop, but then this one would have been a D, and this one would have been a D plus H. Let's just keep it really simple. Again, remember, you can set height equals 0 anywhere you'd like. If you do that, this height over here is going to be 0 because it's at that point right here. This is point 2. And so it simply becomes this. And then the height here is simply going to be h, where this is the h that we're talking about right here. The next question I have is, what's the velocity at this point over here? Well, this is where the small hole becomes important. I'm going to argue that for all practical purposes, the velocity at this point is 0. You might say, well, wait a second, isn't the water level going down? Yeah, but if this is a tiny hole, we're going to say it's about 0. And you'll see why in a second. This is not a major equation, but it becomes simply this. Rho cancels out on both sides. You can move or multiply both sides by 2, and we end up with this equation. What's V2 going to be equal to? It's just the square root of 2gh. And you're like, wait, isn't that the same velocity as an object dropped from some height? Yeah, it is, actually. This particular equation is called Torricelli's theorem. You might say, why isn't it just a law? Well, the one approximation we made was this one right here, where we said that this velocity is essentially zero. And that's pretty much valid. There's this, if it's a large hole and the water is dropping rapidly, you might argue that maybe that's not zero. But it gives us a good approximation for most cases. In fact, this is one of his, or a diagram roughly representing it, how he came up with the idea. If you have a container of water that's sort of being refilled as rapidly as it empties, you'll discover that the water, as it comes out of these holes, goes fastest down here, greater height change, than the ones up here. It's the weakest jet. And he discovered that there was this envelope here at about 45 degrees that described the different streams of the water. Torricelli's theorem is useful. It's a fast way of solving velocity if you need it. Hopefully this all makes sense. Good luck, and here's all the equations for the chapter, just so you've got them. We'll talk to you soon. Bye-bye.